Linear function is what we're going to work with today, and don't make this hard. We're just going to basically look at a bunch of functions and determine if they are linear or if they're nonlinear. Wow. Okay, the key to linear is this word right here. So a linear function is going to look like a line. So the nice thing about it is, even though you might not recognize the word linear, you should recognize the word line, and it's going to make a line every single time. And so if it doesn't make a line, it's not linear. Okay? And I know I see some of, when you guys graph, sometimes you do this, and you try to make a line, but it looks like that. Technically, that's not linear. So try to make it straight so it looks like a line, right? Okay, do the best you can. Sometimes I freehand stuff. And honestly, to make a line, the faster you go, the better. The slower you go, probably the more errors you get. So linear, nonlinear, I can't make this hard. This part I can't make hard at all. Nothing I can do to make it hard. It's either a line or it's not a line. Later on this year, we're going to deal with linear, and I'll give you some more names of different kind of functions and different kind of graphs. But right now, it's just this and this. So it's either a line or it's not a line. This will be on the next test. And somebody's going to miss every single one of them because they forget what this word means. So if you need to study it, seriously, probably 20 seconds, you're good. Right? All right, moving on. It does get a little bit harder. Okay, we might have a table of values, and I don't want to graph every time I see a table of values. I don't want to have to graph it. Okay, that would be very, very annoying to have to just whip out some graph paper every time you have to look at something and determine if it has basically a linear value. Okay, and so this is how we're going to do this. So in order to be linear, you're going to have a constant rate of change. So you're going to have a constant rate of change. Okay, and in this case, the constant rate of change is going to be an addition, only addition. We're not going to deal with anything else, so we're going to do an addition. So let's see if we have a constant rate of change here. To go from 2 to 4 is what? To go to 4 to 6 is what? Do we think that's a constant rate? Are we adding 2 every time? Yeah. Could we continue the pattern? What's next? 10. Just adding 2. Now let's look at down here. What's that going to be? Plus 5. That looks like it's constant too. It's not the same rate of change as this, but is that okay? The x's have to have the same rate. The y's have to have the same rate. This would be a linear example. This would be a linear. Okay. Let's look at this next one. And I can make this a little bit hard, but again, if it looks weird, it's probably not linear. Okay, let's look at the top here. 1, 2, 3, 4. I think I know this one. This one's easy, right? Plus 1, plus 1, plus 1. So far, so good. What's the bottom? Plus 2. What's next? Okay. This one works too. Okay. So this one's also linear. All right. let's look at this one. What's that? Is that all just still plus 2? Okay, this looks linear already. What's this down here? Plus 3? What's that? Is that plus 3? Okay, so you're saying it's times 3 times 3 times 3? Is that linear? I don't remember. Let's go back a page. If I go back a page, it's supposed to be a constant rate of change, and I'm only going to add. And I guess I should add or subtract, because add and subtract is the same thing. So I could do add or subtract. You might want to change that. Some people get confused. I usually say add because subtraction is just adding with negative numbers. So what we determined is this is a pattern, yes. This is not a linear pattern because I'm not adding the same thing, am I? I'm adding 3. I'm adding 12. So this would be nonlinear. Even though it forms a pattern, it is not a linear pattern because I want it to be constant of an addition or subtraction. Does that make sense? All right, we're moving right along. There's just not a lot of notes today because I can't make a lot of this very hard. Let me make sure I'm covering everything that you need today. Oh yeah, here's the last thing. Okay, this is linear. You'll see this later. So I'll give you an example of this. Y equals 3x plus 7. That's linear. Here's the rules for linear. To be a linear function, you're going to have, so this would be yes, linear function. You are going to have, you have a y, and most of the time, an x. I guess I need to write that, not just say it. Okay? You're going to have a y, and most of the time, you're going to have an x. Okay? What you're not going to have, so we'll call this nonlinear. You're going to have exponents. You're going to have square roots or radicals. You're going to have xy's. Okay? For example, like if you had something like this, x plus xy equals y. Well, there's something more to this one. This one's a little more complicated. So basically, linear is less complicated. Anything that looks confusing or weird, like exponents or square roots, that's going to make it nonlinear. That's going to mess with the graph a little bit. Okay? And so that's going to change things. All right, let's do this. Let's see if this is linear. What do we think? Linear or nonlinear? Linear. I don't have anything weird going on, and I have an x and a y. That's good, right? So that is linear. All right, let's look at this. And this one might take a little bit of work. Okay, first of all, when I look at this, this looks complicated. And anytime I see complicated, I'm thinking nonlinear, just right off the bat. Okay? And if there's something you don't know how to do, chances are it's not linear, because all we've gone over this year are basically linear problems. Okay? So I'm looking over here. This is the complicated part, right? Distributive property. I haven't even gone over how to do this year, have I? Okay? But if you did know how to do this, because just by not knowing how to do this, it makes me think it's going to be linear. If you didn't know how to do this, this would be 3 times 4 is 12. X times x is x squared. Okay, I don't need to do any more work. Right there, what does that do to the whole problem? Nonlinear. Later on, we're going to learn that this would be quadratic, but we're not going to do that for a while. And I didn't have room for nonlinear, so nonlinear. So that's all there is to know about linear and nonlinear at this point. Throughout the year, we're going to add different things instead of nonlinear. We're going to add quadratic. We're going to add exponential. We're going to add various things like that. But for now, it's just linear and nonlinear. Okay, so that's most of it. The last little bit of this is continuous and discrete. So I'm going to write down some stuff about continuous and discrete, and then we're going to figure this out. So we're going to have 2 words here, discrete, domain, and then we're going to have the word continuous domain. Of course, we know continuous and discrete domain refer to the x values. Okay, discrete and continuous. All right, I'll read the definition. A discrete domain is a set of input values that consist of only certain numbers in an interval. So I don't want to write that necessarily unless you get it. I'm going to write individual. Well, I'm going to individual points. Individual points. Continuous domain, a set of input values that consist of all numbers in between an interval. Wow. Consist of all numbers in an interval. So basically it is all values in between 2 points. Okay, so those are 2 things. Continuous also could not have endpoints at all. It could go infinite in all directions. But a lot of times this is what we need to know between the 2. And so I'm going to draw a graph. And you're going to tell me discrete or continuous domain. What is it? Heard the right answer. It's discrete. I have individual points. Do you see them? And I bet you can guess what this one's going to be. What is it? It's continuous, right? And basically, I have endpoints, sure, that's okay, but this line represents all the points in between these 2 points, right? So this is continuous, this is discrete. Okay, here's an example of discrete. Okay, how much does a can of, what can you even buy in the cafeteria from the vending? Can you buy a can of like Diet Coke or something?
Yes.
How much does a can of Diet Coke cost nowadays?
$2.
So 1 can costs $2?
$2.25.
Okay, so you just leave the change in there?
No, Powerade is $2.
Oh, Powerade is $2. So it's $1.25 for a can of Coke. How much for 2 cans of Coke? $2.50. What if I have $2? Can I get 1.5 cans of Coke? So this would be discrete. You have to either get 1 can or 2 cans or 3 cans or 4 cans or 5 cans or 6 cans, right? That's how that works. Okay. Let's try to think of something that might be continuous. Okay. How about, does anybody know how hot it is today? So let's just pretend, let's call this at 12 o'clock p.m., let's call it 90 degrees. At 1 o'clock, what do we expect it to do? Get hotter? We're going to call it 93 degrees. At 12:15, could it be maybe 91 degrees? At 1220, could it be maybe 91.2 degrees?
Yeah.
So between these two times, it's going to vary temperature, right? So it's not discrete, it's continuous. And as we continue to go to, we call that maybe 95 degrees, it's going to be a line slightly going up. You know, the graph's going to look like this. We're going to start at 12 at 90, wherever that is, and the line is going to go up as it gets hotter, right? Here, it's just going to be almost look like a stair step. It's going to be dot, 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 because you can only buy 1 can or 2 cans or 3 cans. Here, you can divide it down to, 12:01 in 10 seconds, right? You're going to have a degree. That's the difference between continuous and discrete. And I think that is all she wrote as far as the notes. I'm turning this off. I'm going to give you your work.